Hi, I'm Bob from National, and I'm here to show you how a SEPIC converter works. So, SEPIC converter, this is a conceptual schematic, generally uses any boost type controller. The SEPIC is primarily used where an input voltage could be above or below the output voltage. So, let's say, for example, we're going to try to design a circuit from 5 volts to 15 volts input, and we want to produce an output voltage of 10 volts. That would be the perfect type of range for a SEPIC converter. So the SEPIC converter is basically, it's a buck-boost derived topology. The classic buck-boost is an inverting topology, which has an output voltage that can be above or below the input, but it's of negative polarity. The SEPIC converter solves that problem so that we can have an input voltage that's positive while we also have a positive output voltage. The SEPIC converter is characterized by the use of 2 inductors, one going to the input and one going to the ground. These are connected by a coupling capacitor, which basically shorts the AC signal from one inductor to the other inductor. Effectively, this puts L1 and L2 in parallel for an AC point of view and for the power transfer. So here we're showing the classic uncoupled SEPIC, where we're using 2 discrete inductors and a coupling capacitor. Generally, the coupling capacitor should be sized so that it does not produce a significant voltage droop at the switching frequency. So operation of the SEPIC is such that when the primary switch is energized, energy is stored in the input inductor and in the output inductor, which is connected by the coupling capacitor. When the switch is open, energy is transferred through the coupling capacitor, the rectifier diode, and to the output capacitor. Okay. So one of the issues with designing separate inductors on the SEPIC converter is the fact that these 2 inductors with the capacitor form a resonant circuit. And as we all know from circuit theory, for a step response on an LC circuit, the voltage can rise to twice the applied voltage on a transient basis. So if this is Vn, this voltage can rise to 2 times Vn. Now, this might not be desirable for a lot of applications. The only thing that damps that is any series resistance that is in the circuit in series with the LC. One way to overcome that is to design a SEPIC that has the inductors coupled. So we've got 2 windings coupled. The dots show the polarity on the same core. So when we do that, these inductors are now coupled on the core, and the energy is coupled through by the SEPIC coupling capacitor. Without the coupling capacitor, this would operate like a flyback converter. With the coupling capacitor, that shorts anything that would be stored in the leakage inductance between these 2 windings and allows for a much more efficient operation. The SEPIC with coupled inductors is restricted by the fact that both of these inductors must be the same value, so that L1 must equal L2. What we find in practice is that there's a limited range of coupled inductors that we can find as off-the-shelf components. So unless we're willing to go with a custom inductor, we may want to go back to the SEPIC with separate inductors. If we don't like the fact that on a transient the input voltage can rise to approximately twice Vn, there's a way that we can use this with separate inductors and damp this circuit with the high-value ceramic capacitor. And what we do is we add a damping network across the SEPIC capacitor using a discrete capacitor, and a discrete RC is placed across the coupling capacitor. This can typically be an aluminum electrolytic. The value is about 5 times CS. This resistor is selected to damp the circuit for a non-oscillatory behavior. Okay, so let's take a look at a practical circuit design. Over here, we have a SEPIC using an LM3481, which is a standard boost controller, and it's set for a 500 kilohertz switching frequency. The input voltage range for this circuit could be anywhere from about 4.5 volts to 18 or 25, depending on the selection of output voltage. So for this boost controller is a current mode device. It drives an external MOSFET, uses a current sense resistor in the MOSFET source, and feeds that current signal back to the control chip. From the MOSFET, we see the drain connection goes to the SEPIC coupling capacitor, to the input inductor, and to VN. For this particular example, we're using a coupled input inductor. Couples the primary side inductor and the secondary side inductor. That connection goes to the output rectifier diode, to the output capacitors, and then to the output voltage. The key point in looking at the practical design is the design of the switching current, or the primary switching current path. Switching current has to travel from the MOSFET through the SEPIC coupling capacitors, through the output rectifier diode, and through the output capacitor back to ground. So this is the primary switching current loop. In practice, this should be made as tight as possible to keep from producing a lot of output ripple on the output voltage. For more information on SEPIC design and for more information on power products in general, visit national.com/power.